So as far as the electrical driving force, it's going to then take into account the membrane potential, right, which is essentially the degree of unequal distribution of anions and cations. So if we have lots of positive charge in one area and lots of negative charge on one area, that is a separation of charge. That is an unequal distribution of the various charges. And so that's going to be a source of energy. That's going to be potential energy to be able to move those particles based on their different charges. And then we also can think about the magnitude of that membrane potential. How strong is it? That's going to depend on a couple of things. It's going to depend on the type of charge, right? Some cations are positively charged, 2+ like calcium or 1+ like sodium. So that number of charge on the particle will determine the magnitude or the strength with which particles want to move. We're going to represent that value in terms of millivolts, and that's really going to be determined on the polarity of the cell. So we're going to describe the magnitude of the membrane potential with reference to the inside of the cell. We're always talking about the inside of a cell. So when I tell you that a resting cell has a membrane potential of -70, I'm telling you that the inside of the cell has more negative charge, 70, so more negative, than the outside of the outside of the cell, which has more positive charge. So when we describe the membrane potential, we're always referencing the environment or the charge or the polarity that's on the inside of that cell. And for that reason, at rest, we want to describe what's happening in a cell. At a resting state, the inside of the cell is always going to be more negative. We can think about this later on in some of the future chapters when we look at the action potential when we excite the cell. So the cell is no longer resting, it's now excited. This will change and the inside of the cell will become more positive or positively charged. And so we want to think about what's happening at a resting cell so that when we get to looking at our neurons and how we can excite them, we will then have to change that negative potential to excite the cell. All right. So this schematic here is a good way to represent that. We've got the excess cations. This is going to be outside of our cell. Notice that there are more positively charged particles than there are negative. On the other end, so this is inside the cell, we've got more negatively charged particles or more anions than there are cations, okay? So there isn't only anions inside and only cations outside. Really important to make that distinction. It's just that there's unequal distribution. So there's more or excess anions inside and excess cations on the outside. Okay, and then also just to point out where the plasma membrane comes into play. So because of that phospholipid component of the plasma membrane, it really nicely helps to separate these two compartments so that we can have an excess of anions inside and an excess of cations on the outside. If we didn't have a plasma membrane, both the intracellular and extracellular fluid compartments will have the identical environments in terms of charge and in terms of the membrane potential, and we would have zero membrane potential, right? If there's no difference in the charge, there is no membrane potential, okay? And the membrane potential is really important to the function of the cells, especially cells like neurons, where we'll see have the ability to get excited and to relay various types of communication. All right. I'm going to skip over this because we did do a drawing to describe the electrical driving force. And then here's a really nice video. If you haven't watched this already, please take some minutes to do so. That really simplifies the chemical, the electrical, and then how we can combine those, which we'll talk about coming up, to make the electrochemical. Okay. Let's talk about the magnitude of the driving force. Okay, how strong that urge to move particles across the membrane is. It's also going to be determined by the amount and type of charge on the particle in question. Okay, for instance, is that a cation? or is that an anion? Okay. It's also going to be dependent on the amount of charge, and not just the type of charge. This is the type of charge, right? Whether it's positive or negative, but the amount of charge as well is also important. So that is whether or not the ion is divalent or monovalent. So monovalent means it has one charge, or divalent, meaning it has two charges. So divalent, meaning it has two charges. Okay, so all of this will determine the magnitude of the electrical driving force. All right, so let's illustrate that with a few cell scenarios down here. So here's one cell, here's another cell, here is a third cell. Okay, if we think about sodium moving, all right, so remember our cell is going to have, we're thinking about the movement of sodium, all right? And if the inside of the cell is negatively charged and the outside of the cell is positively charged, we can establish that sodium wants to get to the negative environment, so it has a positive charge. It wants to get to the negative environment inside the cell. And so the membrane potential of this cell environment would be negative 60 millivolts. Okay, so that's our first hypothetical scenario. Let's consider a different scenario here. Let's say we had more negative charge. So instead of just one here, we have twice the amount of negative charge inside the cell. All right. Also, we've got twice the amount of positive charge on the outside of the cell. So we now have more anions inside the cell, and we have twice the amount of cations on the extracellular environment. So now what we see here is that sodium really wants to get into the cell, all right? Sodium really wants to get into the cell. There is a stronger degree of separation of charge. There are more cations outside and more anions inside, all right? So here we can think about the membrane potential as being twice what it was in this first scenario. So it's going to be negative 120 millivolts, okay? Everyone understand how we double the membrane potential? So based on the larger degree of separation of charge, we now have a larger or stronger magnitude of the electrical driving force, okay? All right, now let's think about a third scenario here. Now we've got a different ion altogether. So we've got positive charge outside, negative charge inside. And now we've got an ion like calcium, which is divalent, right? It's got 2+ charge. Who can predict the membrane potential in this third scenario? What do you think this will look like? What will the membrane potential here look like if we've got this scenario set up, but we're now thinking about a divalent cation like calcium? What are we thinking here? Any thoughts, any guesses? It's okay to guess. Do you think it's going to be 60, negative 60? Do you think it's going to be negative 20? Do you think it's going to be more or less than any of those values? Okay, so someone's saying positive 120. Okay, it's a good guess. Right, so that's very close to correct, but this will just be negative, right? So it will in fact be negative 120, okay? So 120 is in fact correct because we're thinking about 2 times the charge here. So it's not going to want to move in the same magnitude as sodium because it has an additional charge, it has an additional positive charge. So it's going to want to move twice as much as sodium would, right? So in the scenario where we have this same degree of separation of charge, right, as we saw in this first scenario, the cation is going to double its magnitude of movement, and it's going to really want to get into the cell. If we were to mimic calcium in this scenario, we would again double that value, right? So it would be 240 negative because calcium would have that 2 charge instead of 1. Okay. So this is just the way that we can identify and determine the exact degree or magnitude of the driving force, the electrical driving force. Okay. All right. So on that basis, we can begin thinking about the electrochemical driving force. This is the total force acting on particles. And in order to do this, we want to combine the 2 forces. So we want to combine the chemical driving force that's acting on the particle, and then we want to also think about the electrical driving force that's acting on a particle. And I want to reiterate here that the forces are not acting separately. They're acting together on a single particle. Potassium, for example, it's going to be moved in both directions because a chemical force is acting on it. At the same time, an electrical force is also acting on it. And so we're going to see potassium move in both directions because both of those forces are acting. And then it's going to level out at equilibrium, which will be the total sum of both of those forces acting. Okay. So we can think about the equilibrium potential as being the membrane potential at which the particle is no longer moving because both of the forces have evened out. And so for potassium, for example, its equilibrium potential is negative 94 millivolts, right? So let me say that in a different way. What that means is when the membrane potential is at negative 94 millivolts, in other words, there's more negative charge inside the cell than there is on the outside, 94 being that magnitude, then potassium is no longer moving. It's at equilibrium because the forces acting on it have evened out. All right. So if the chemical and electrical forces are acting in the same direction, we want to think about just adding them together. Okay. So very much different from this scenario that we just saw here, where the forces are acting in opposite directions. Let's say potassium's chemical force was also moving inside the cell. We would just add those 2 values together. We would get a bigger value, and that would be the sum total of our electrochemical driving force. Okay. If the chemical and electrical forces are acting in opposite directions, we're going to look for the direction of the stronger force. So the direction of the stronger force, we will then subtract the direction of the smaller force from that stronger force, and the particle will be moving in that direction of the stronger force with a smaller degree. And if you think about this, this makes sense. If I have one force pulling an ion outside of the cell, and I have an opposite force pulling the ion inside of the cell, I'm just going to subtract those 2 values. I'm going to take the bigger force, I'm going to subtract the smaller force from that, and I'm going to get, 1, the direction, the overall direction of that particle, which would be in the direction of the bigger force, and then I'm going to get the degree or the magnitude with which that particle wants to move, and that will be a smaller value because I have to subtract the opposing force. Okay, so we simply subtract the smaller force from the larger force, and then the overall direction would be in the direction of the stronger force. All right, now I've got a quick question here to see how much we understand this. So if a chemical gradient existed, under which conditions would a particle not be transported across a membrane if the membrane were permeable to that particle? So what conditions would have to exist for a particle to no longer be moving if a chemical force or gradient is acting on that particle? What conditions would have to exist for a particle to no longer be moving if, one, the membrane is permeable to it, and two, there is in fact a chemical gradient that is existing in that particle? What would have to be true in order for the particle to not move? So someone's saying it has to be at equilibrium or even, which is absolutely correct. So that is perfectly correct, well said. The particle would have to be at equilibrium, and in order for it to be at equilibrium, the opposing forces must be equal. So the chemical force is acting on it. This means there must also be an electrical force that's acting on it in the exact same magnitude. So a chemical force, let's say a degree of 50, and then electrical force, a degree of 50, and now the particle will not move because it has two opposing forces pulling it in either direction, and it can be said that it's now at equilibrium because it's not moving in either of those directions as both forces have evened out, okay? And so that's really what the equilibrium potential is. And so when an electrical force is equal to but opposite the direction of the initial chemical force, we now have zero movement. That particle will be said to be at equilibrium.